Okay, very good morning, one and all. So, in the last class, we studied the advantages of digital communication system over analog communication system. Okay, so let us revise this before the other students join. Okay, so because only 18 students joined till now. And coming to the advantages, so what are the advantages of digital communications? And we discussed that the corresponding because of the presence of source encoder and channel encoder. Okay, so because of presence of source encoder, the signal can be represented in the form of zeros and ones. Okay, so once it is represented in the form of zeros and ones, you are encoding the data. Okay, mean that you are compressing the data. So once you compress the data, the redundancy can be overcome. Okay, so that is mainly due to the presence of channel encoder and source encoder. Because of channel encoder, we are adding some sort of k number of check bits to the n bit binary sequence obtained from the source encoder. Okay, so once you add these check bits, we can be able to detect and correct the error bits. Okay, so that's why digital signal, if we make use of digital signal in the communication, so obviously we can be able to detect and correct the errors, and and also the signal can withstand with noise. Okay, because because multiple number of repeaters were present throughout the channel, that will regenerate the original component by removing the noise. Okay, so and similarly the hardware implementation of the digital signal is flexible. Okay, so that's why digital signal is preferable. And digital signals can be coded with low error rates because of the presence of channel encoder, its high fidelity and privacy. Why privacy? Because you are encoding the data, and you are adding some certain check bits at the code encoder, so that unwanted people cannot capture our data. Okay, so similarly because of high bandwidth for the digital signal, because once the digital signal possesses a higher bandwidth, so how can we, once the digital signal possesses the higher bandwidth, because already we discussed in the last class that digital signal has like a drawback that it possesses higher bandwidth for transmission purpose. Okay, so to overcome that problem, here the SNR is maintained in trade-off with the bandwidth. Okay, so once we provide some sort of trade-off, we can be able to handle the bandwidth problem of digital signal. Okay, so similarly all the digital modulation techniques use TDM for multiplexing as a multiplexing technique, and we have once the synchronization is good, obviously TDM, once we use TDM technique, so it is very good to multiplex the digital signals using TDM compared to FDM, compared to analog component. Okay, so in the similar way, like signal storage is easy because you are encoding the data in the form of zeros and ones, and there is no loss during data recovery because of the presence of regenerative repeaters. And last but the important point is the cost gradually reduces to half for every 2 to 3 years, but its performance doubles over the same time period. Okay, these are some of the advantages of digital communication over analog component. Okay, and only main drawback is it needs large amount of bandwidth, but to compensate that we are providing a trade-off. In the last slide we have seen is Shannon-Hartley theorem, which is channel capacity is represented in terms of bandwidth and SNR. Okay, so we can be able to compensate that problem. Okay, so all these things we studied in the last class, the advantages and disadvantages. Okay, so in the today's session we can discuss the elements of pulse code modulation. The elements of pulse code modulation, and let us see what are the elements. Okay, so these here we mentioned sampling, quantization and coding, because we are converting the analog component into digital component. Because what is the input to the PCM? The input to the PCM is analog signal. So input to the pulse code modulation is analog signal. That analog signal is converted into digital by using sampling, quantization and encoding. Okay, now let us see what are the elements in detail in this today's session. So this is the third module of the first chapter. So after completion of this elements of PCM, each and every student should be able to distinguish and identify the importance of all the elements present in the PCM. Okay. And coming to the pulse code modulation. Okay, and let us see. So what is pulse code modulation? So it is one of the modulation. Is this, please go through the slide. Okay, pulse code modulation. Okay, so what is meant by pulse code modulation? Analog signal is represented in the form of code. Okay, this is the first type of, regarding your syllabus, this is the first type of pulse analog modulation techniques. Okay, what is the first one? Pulse code modulation. It is the digital representation of sampled analog signals. It means that the input is the analog. Input is nothing but the message signal. So message signal is analog in nature, and that analog component is converted into code format with the help of pulse code modulation. Here pulse code modulation, it means that input is initially analog in nature, that is converted into digital sequence by the help of this pulse code modulation technique. Okay, so what is the input to the PCM? Analog signal. What is the output? Encoded data sequence. Encoded data sequence. Okay, now so if you observe the, please observe the waveforms. If you observe the waveforms, here we have input as sinusoidal waveform. So nothing but here the message signal is analog in nature. Okay, so that analog component is converted into this output. Here you can observe the second waveform, that is a PCM output. It is nothing but a data sequence which is in the form of zeros and ones, which is in the form of zeros and ones. Mean that in the case of PCM, the sinusoidal waveform is converted into code format. So what is PCM anagane? You should recollect that the analog signal is converted into digital. Okay, so mean that A to D conversion is going on there. Okay, so how can you convert analog signal into digital? So we studied it in the earlier classes. So how can you convert analog signal into digital? We can convert analog signal into digital by making use of 3 steps. Okay, first one is sampling, second one is quantization, third one is encoding. All these things we studied in the last classes. Okay, so anyhow we can discuss it in detail about all the things in the PCM module. Okay, so what is PCM? PCM is a digital representation of sampled analog signals. Input is a message signal and input message signal is analog in nature, and the PCM output will be a code sequence. Okay, this is about the first point in this slide. So next let us see the applications. So what are the applications of PCM? So will you feel that PCM is using anywhere? Yes. Okay, here are some of the applications. So digital audio recorder. So what this digital audio recorder will do? So it will record the audio signal, okay, or the sound signal, and it will store the signal in the form of like zeros and ones. Okay, so our audio signal is stored in the form of digital data and zeros and ones. Okay, so that is the first application. What is the first application? Digital audio recorder. So audio signal is stored as a digital sequence. Our voice audio is nothing but like our voice signal. Okay, so our voice signal is stored as a digital component, okay, in the form of zeros and ones. Okay, and second one is CD, compact disc. Okay, so here you are storing the data as a digital component. Okay, data is stored as digital. Data is stored as digital. That is CD. That is the second application of PCM. And what is the third application? Digital telephony. So digital telephony. So like a pulse switching telephone network, that is the first implementation of digital telephony. So in the case of digital telephony, what is going on actually? So like in the traditional telephony, em jarugutundi, audio signal is digitized. Okay, so if you make use of general mobile phones, what they will do, or landline, what they will do, they will convert our voice signal or audio signal into in the form of like digital component, in the form of a digital component. And that best first implementation of the digital telephony is PSTN, public switching telephone network. Okay, so in this PSTN, like each and every mobile, okay, each and every call you can say, okay, so that's one type of, each and every mobile number. So you have one mobile number, each and every mobile number is considered as one line, public switching telephone network, that is generally defined as one network. Okay, public switching telephone network. So అదే మనం జనరల్ టెలిఫోన్ ని తీసుకున్నారనుకోండి, ల్యాండ్ లైన్ టెలిఫోన్. సో లైక్ ఈచ్ అండ్ ఎవ్రీ వైర్ లింక్ is a connection. Okay, and that is nothing but given with your phone number, mobile number or landline number. Okay, so that is the initial implementation of traditional telephony. Nowadays it too has been upgraded into mobile communications. Okay, so these are few applications of PCM. Okay, so what is PCM? So please go through this slide once again. So what is PCM? PCM is a digital representation of sampled analog signals. It means that the analog signal or the input message signal, which is sinusoidal in form or analog in form, is converted into digital sequence or data sequence or binary sequence. Okay, so that is in the form of zeros and ones. Simply to say, PCM is analog to digital converter. We can say analog signal is converted into digital. Okay, or analog component is converted into zeros and ones. Now, what are the applications we discussed? Digital audio recorder, where sound signal is stored as digital, and our voice signal is stored in the form of zeros and ones. Okay, and if you observe CD, compact disc, where the data is stored as digital. Okay, so what that CD will do, we are storing some sort of data. Okay, so you want to say store some files. Okay, so that files can be stored in the form of digital data. Okay, in CD. Okay, that is another application. And digital telephony is the another application where you will have audio signal digitalization. So like our voice signal is digitalized. So like these are some of the applications of PCM. Now let us move to the next slide. Now this is the like according to your syllabus, we can call this as the block diagram of PCM, where you will have multiple number of elements in the transmitter section, receiver section, and in the channel, Okay, so let us observe the PCM transmitter section. So in this slide you can observe three sections. I represented the top one as PCM transmitter section. Like in the middle you will have we have represented it as two. Second one, that is channel, or you can also call it as a transmission path. And third one is PCM receiver section. Third one, the bottom one is PCM receiver section. So in the PCM transmitter, if you observe what is going on actually, analog message signal. So always remember that the input for the PCM is analog signal. Okay, message signal is analog in nature. Okay, that analog signal should be converted into digital data. Okay, so that like the principle, that is the principle of the PCM transmitter. That is the principle of PCM transmitter. So what is the importance of PCM transmitter section? It converts the analog signal into pulse code modulated form. That is nothing but a binary sequence. That is nothing but the binary sequence. Okay, so the analog signal is converted into digital sequence using the 4 steps. Okay, simply to say 3 steps only. And this low pass filter, if you observe the low pass filter at the transmitter, so every student is familiar with the why we are using a low pass filter at the transmitter section. So can you explain why low pass filter is used at the transmitter? Any one of you, can you please respond to me? What is the importance of low pass filter at the transmitter? Any one of the student. So what is the importance of low pass filter? Low pass filter eliminates the higher frequency components. Okay, so which frequency components you want to transmit? Only the message signal frequency component. Let the message signal frequency component be, let the maximum message signal frequency component be some FM. Okay, so that frequency only should be allowed through the transmitter, but not all the higher frequency components. Okay, so that higher frequency components must be attenuated before entering into the transmitter section. So what is the importance of low pass filter here? Low pass filter eliminates all the higher frequency components to overcome the problem of aliasing effect. So what is aliasing effect? So always the sampling rate should be greater than or equal to twice that of the sampling frequency. Okay, so to overcome that, here low pass filter is used. So here low pass filter is used to attenuate all the higher frequencies prior entering into the transmitter section. Okay, so what is the importance of low pass filter? Low pass filter eliminates the frequencies greater than FM. I can say that low pass filter eliminates the frequency components greater than FM, where FM is the like frequency of the maximum frequency component of the message signal. Okay, next the output of the low pass filter, which is only the message signal frequency component, is applied to the A to D conversion process. Okay, which includes the sampler, quantizer and encoder. Okay, so already we discussed some points regarding the sampler. So what the sampler will do? Already in the last classes we so many times we repeated the same point. So what is a sampler? Sampler converts the continuous amplitude, continuous time signal, that is nothing but the analog signal, into continuous amplitude discrete time signal. This sample signal is nothing but continuous amplitude but discrete in time. Okay, that sample signal is converted into quantized form with the help of quantizer. But what is quantization? It is a process whereby the amplitude axis of the message signal, is discretized. Okay, is discretized into 2 power n number of levels. Into how many number of levels? 2 power n number of levels, where n is the number of bits you want to encode. Here we are representing PCM output. For example, let that PCM output consists of n number of bits. Okay, let us assume that PCM output is a n bit sequence. If PCM output is a n bit sequence, how many number of bits are there at the encoder? N number of bits. Then quantizer divides the amplitude axis into 2 power n number of levels. Into how many number of levels? 2 power n number of levels, where n is the number of bits you want to encode. Okay, so the quantizer divides the amplitude axis into 2 power n number of levels. Nothing but quantizer is discrete. It's making the amplitude axis as discrete. Okay, so that is applied to the encoder based on the discrete amplitude and discrete time of the quantizer signal. Encoder generates the output in the form of binary sequence. Now that is final PCM transmitted signal. Now that PCM transmitted signal is applied to the transmitting antenna. The data, once it is allowed through the channel, sometimes our signal may gets corrupted with a noise. Okay, so the distorted PCM signal once it is allowed through the channel, we already discussed so many times that in the channel or in the transmission path, we have more number of regenerative repeaters. Please observe the block diagram. So there are multiple number of regenerative repeaters in the channel. So what each and every repeater will do? So here each repeater will every time equalize the output signal with the input signal. How it will perform the equalization? It considers a threshold value. Okay, so that please always keep it in mind that the threshold value is nothing but the predefined input magnitude. Okay, so every time the present received signal magnitude is compared with the input component magnitude, or simply to say with the threshold value. If it is compared with the threshold, and the component beyond the threshold will be considered as noise, and that will be eliminated with the help of regenerative repeaters. So see, we mentioned so many dots in between the repeater to repeater. It means that in the channel we have so many number of regenerative repeaters. So like this, if you consider like in general, if you consider even in the, if you transmit the electromagnetic wave or the PCM data into atmosphere, there we'll have so many repeaters in each and every location, like specified locations. We have, they will construct the repeater, or they will add the repeater circuit. And so in the channel we have a multiple number of regenerative repeaters which will regenerate the original signal. Okay, so that those are normally called as repeaters. And why they are specified as regenerative? Because it will regenerate the original signal. It will regenerate the original signal. Now please observe the output of the repeater. It is a regenerated PCM signal. What is the input for the repeater? Distorted PCM component. Okay, because in the channel signal gets corrupted by noise. Okay, so many regenerative repeaters are there in the channel. So finally that is collected by the receiving antenna, and it is applied to the regeneration circuit. Okay, once again to get the PCM received PCM signal. Okay, so now once again you need to at the receiver section, once again you need to recover our original component. How can we recover original component? With the help of decoder and a reconstruction filter. See, always remember that the decoder functionality is opposite to that of encoder, and the reconstruction filter is nothing but the low pass filter. Once again it will allow only the lower frequencies by eliminating the high frequency component. So the decoder functionality is opposite to the encoder used at the transmitter. Okay, so these are the elements of pulse code modulation. Okay, so it consists of 3 sections in general. So PCM transmitter section once again consists of low pass filter followed by A to D converter. So what is A to D conversion? A to D converter is consists of 3 sections, namely the sampler, quantizer and encoder. Okay, and next in the channel we have regenerative repeaters, and in the receiving section we have decoder followed by reconstruction filter. That reconstruction filter is nothing but the low pass filter. Okay, is this block diagram clear to everyone? See, please one of you respond. Is this block diagram okay? Shall we move to the next slide? Okay, ma. Anyhow, we'll discuss about each and every element in detail in the next slides. Okay, so now let us move to the next slide. So coming to the low pass filter. So already I said you what is the importance of low pass filter. It eliminates the high frequency component present in the input analog signal. Okay, so greater than FM frequencies will be eliminated because FS should be always greater than or equal to 2 FM. Okay. Okay, so low pass filter eliminates the higher frequency component present in the input analog signal. Okay. Next, let us move to the sampler. So what is the importance of sampler? So this is about the low pass filter which will eliminate the higher frequency components. Okay. So here low pass filter is generally used to overcome the aliasing problem. So generally aliasing problem occurs whenever the sampling frequency is less than 2 FM, less than 2 FM, where FM is the maximum frequency component of the input signal, where FM is the maximum frequency component of input signal. So what is aliasing problem? Aliasing problem is nothing but the overlapping of lower frequency components with the higher frequency components. Okay. So once this type of overlapping occurs, generally the lower frequency signal will get disturbed with the higher frequencies. That's why high frequencies must be eliminated prior entering into the transmitting section. Okay, so that's why low pass filter is used here. So the input low pass filter eliminates the aliasing problem, okay, by removing the higher frequency components. So what is the importance of input low pass filter? We have output low pass filter also. That output low pass filter is used as a reconstruction filter. And what is the importance of input low pass filter? Input low pass filter generally overcomes the problem of aliasing effect. So what is aliasing effect? Aliasing effect is the overlapping of higher frequency components with the required frequencies. Required frequencies are the low frequency component. Okay. So that's why always the high frequency components must be eliminated prior entering into the transmitter section. Okay, this is about the low pass filter. Now let us move to the next slide. What is the next block? Sampler. So in the further slides, we will discuss about each and every element of the PCM in detail. So what is a sampler? Sampler converts the continuous amplitude, continuous time signal into continuous amplitude, discrete time signal into discrete time signal. Okay, so it's generally common terminology in all the pulse modulation techniques because we'll discretize the time axis. We will discretize the time axis, and already we know that if we want to discretize the time axis, okay, so you need to divide it into time slots having a sampling interval t suffix s. Okay, please observe this slide. Fourth point. So what is the sampling interval? Sampling interval is Ts. Okay. So where Fs can be represented as the sampling rate or the sampling frequency, which is the reciprocal of sampling interval. What is Nyquist rate? Nyquist rate is the cutoff point. Okay. Up to which if Fs goes below 2 FM, the signal cannot be recovered properly at the receiver. Okay, so always Fs should be greater than or equal to 2 FM, and the cutoff is generally called as the Nyquist rate. It is nothing but the minimum sampling rate. Minimum sampling rate. Okay, so what is the maximum frequency component? FM. Okay, FM is the maximum frequency component of message signal. So always the message signal is it is a band limited signal. How can we define the input analog signal? It is a band limited signal that range from minus omega m to plus omega m, minus omega m to plus omega m. Okay, so when aliasing problem will occur, whenever fs is less than 2 fm, aliasing problem will arise. Okay, so to overcome that aliasing problem, always fs should be greater than 2 fm. So this is about the sampling, and I think each and every student are familiar with all the points I mentioned here, because you studied so many times these points. Okay, so analog signal is discretized with a sampling interval of Ts, and the sampling rate is the reciprocal of sampling interval Fs. Okay, and what is the Nyquist rate? Fs is always equal to 2 fm, and proper recovery, always Fs should be greater than or equal to that of Nyquist rate. Okay, but whenever Fs goes below 2 fm, what will happen? The low frequency component, that is plus or minus omega m component, gets overlapped with the unnecessary higher frequency components. Okay, so that problem is generally called as aliasing effect. So we can overcome that aliasing effect by considering the sampling rate greater than or equal to Nyquist rate. Okay, this is all about the sampler. In the next slides, we can discuss the types of sampling. Okay, so even we discussed it in the general classes of analog communication regarding these types of sampling. So we can discuss it here. Okay, once again I will revise all these things, because there is a chance that you may get these questions in your external examinations. Okay, so what are the various types of sampling? Did you remember? Did any one of you remember what are the various types of sampling? Generally, 3 types of sampling techniques are there. Okay, sampling is nothing but conversion of analog signal into discrete time signal. Okay, so how many types of sampling techniques are there? In general, there are 3 types of sampling techniques. What are the 3 types? Ideal sampling, which is also called as impulse or instantaneous sample. Okay, so it is ideal in nature. Okay, and that is second one is natural sampling, which is also called as gating. And the third one is flat top sampling. Out of these 3, we know flat top sampling is the best sampling technique when compared to the first and second type of sampling techniques. Let us, so how many types of sampling are there? In general, there are 3 types. First one is ideal sampling, which is also called as impulse or instantaneous sampling. Second one is natural sampling, which is also called as gating. And the third one is flat top sampling. Okay, so because of flat tops for the pulses, or because of having flat tops for the sample signal, flat top sampling is generally preferred compared to the ideal and natural sampling. Let us go through the waveforms for each and every sampling technique in the next slides. Okay, so we are moving to the next slide. Now, let us see here. So what is the first type of sampling? Ideal, impulse or instantaneous sampling. Okay, so what is the principle behind this? Please all of you remember only the principles of the 3 types of sampling. So what is the principle behind the ideal sampling? So whenever you multiply the signal, what is the input signal? Continuous signal. Okay, what is the input signal to sampler? Analog signal, which is band limited to plus or minus FM, because higher frequency components are eliminated by the low pass filter. So what is the input for the instantaneous sampling or any kind of sampler? Band, you need to specify that band limited message signal. Band limited message signal and endu cheppali. Band limited because you used low pass filter at the transmitter section, which eliminates the frequencies beyond FM. Okay, so input message signal is a analog signal or continuous signal which is band limited to plus or minus FM. Its frequencies range from minus FM to plus FM. okay, but not beyond plus or minus FM. So beyond the negative frequency minus FM and beyond plus FM, there is no signal component. Now, so let us see the principle behind this. So what is the principle behind ideal sampling? The principle is always x of t is multiplied with a series of impulse train. Series of impulse train. Let us represent that impulse train as x delta of t. Sorry, please observe the the circuit shown there. Second point, please observe the circuit. X of t and x delta of t are the inputs to the multiplier. So whenever you multiply x of t with series of impulse train, then you can generate the ideal sample signal. Ideal sample signal or impulse sample signal or instantaneous sample signal. Why it is called as impulse sampling? Because you are multiplying with series of impulses. Okay, so why we are calling it as impulse sampling? Because you are multiplying it with series of impulses. So impulses are located at where these impulses are located? At the sampling intervals. Okay, so at the sampling intervals, the impulses are located. Okay, so x delta of t is a series of impulses located at respective sampling intervals like 0, ts, 2 ts, 3 ts, 4 ts, 5 ts, 6 ts, 7, 8. So in this figure, if you observe, it ranges from 0 to 8 ts. Okay, so those are the respective sampling intervals. So series of impulses are located at the particular sampling intervals. Now the signal x of t, what is x of t? Input continuous signal or analog signal is multiplied with impulse train. In the figure, the pink one is the impulse train. Pink impulse train. Okay, so analog signal is represented with dots, x of t. Okay, impulse train is x delta of t. If you multiply those two, how you will get? You will get the resultant shown in the figure. It is directly the product of the impulse train and the analog signal. Okay, now what is the output here? Xs of t. X suffix s of t is nothing but the what is it? That is a sample signal. Which sample signal? Ideal sample signal. Now, why it is called as instantaneous sampling? Why we are calling this as instantaneous sample? Because the output of the ideal sampling occurs only at instantaneous levels. Ante only at 0, ts, 2 ts, 3 ts, 4 ts, like that it occurs only at the output occurs only at instantaneous levels, because impulse occurs at within almost all you can say at one particular instant. Impulse will occur only at particular instant. Okay, so it won't occur for a longer duration. It occurs at particular instant point or particular interval. Okay, that's why it is also called as instantaneous sampling. Okay, now why it is called as ideal sampling? Why it is called as ideal sampling? Because the generation of the series of impulses is very difficult. The generation of series of impulses is very difficult. That's why it is called as ideal sampling. Now I think that everyone is familiar with the terminology used there. Why it is called as ideal sampling, and why it is called as impulse sampling, and why it is called as instantaneous sampling. Okay, so anyhow, how can you generate the sample signal? Output signal ela vastundi manaki? You can generate the sample signal by taking the multiplication of input analog signal with series of impulse train with series of impulse train. Okay. So we can generate the ideal sample signal by taking the product of the input signal with the series of impulses. Because the generation of series of impulses is like difficult one, it is called as, practically it is difficult. Okay. So that's why it is called as ideal sampling. And why it is called as impulse sampling? Because you are using impulses. Why it is called as instantaneous sampling? Because impulses occurs at only instantaneous intervals, instantaneous points. That is, impulses occur only at sampling intervals at 0 ts, 2 ts, 3 ts, like that. That is represented here with pink vertical lines. Okay. So here pink vertical lines represents the output. Pink vertical lines here represent the output. But all impulses are in general, like with here a series of impulses if you consider, those are of all of constant amplitude. But here in the figure, pink lines represent the output or the sampled signal. Okay, the output signal xs of t. Xs of t. So how, please observe the third point. Please observe the third point. The series of impulses is x delta of t. You can represent the series of impulses located at various intervals ranging from 0 to nts as t minus nts. Okay. So impulses are located at various intervals. Impulses are located at various intervals. So x of t into x delta of t is summation n equals to minus infinite to plus infinite del of t minus nts. Here del represents the impulse function. Okay. And the instants are at t equals to nts. Okay, where n ranging from minus infinite to plus infinite. Okay, so the series of impulse train is generally represented as del of t minus nts, del of t minus nts. Now if you multiply that with x of t, you can generate the sample signal. The equation represented in the third point is the time domain description of ideal sample signal, is the time domain description or time domain representation of sample signal. Okay. And the fourth point, we can see the frequency domain description or frequency domain representation of the signal. An impulse located at various intervals of ts ranging from minus infinite to plus infinite. If you want to represent that in frequency domain, we can represent as 1 by ts summation n equals to minus infinite to plus infinite whenever there is a shift in time. Okay, in time domain description, if there is a shift, okay, so the same shift can be represented as the multiplication of exponential term in frequency domain. Okay, so that's why you will have e power plus j n omega s t, where omega s is 2 pi by ts, 2 pi by ts. Okay, so this is the time domain description and frequency domain description of ideal sample signal. Is this slide okay to everyone? So why it is called as ideal sampling? But this is the first type of sample signal, that is ideal sampling, instantaneous sampling or impulse sampling. Okay. And how can you generate ideal sample signal? We can generate ideal sample signal by taking the product of input analog signal or continuous signal with series of impulses. Then you can generate xs of t. Here x delta of t is series of impulses. Okay. These series of impulses are shown with constant magnitude. Okay. If that is multiplied with x of t, you can see the result in the third point. Xs of t is x of t into summation n equals to minus infinite to plus infinite del of t minus nts. Now the same is represented in the frequency domain description, because a shift in the time we have in the frequency domain we will have multiplication with e power exponential term, that is e power j, same shift, j n omega st, where omega s is defined in terms of the sampling interval as 2 pi by ts. Okay, this is about the first type of sampling, ideal sampling or impulse sampling or instantaneous sampling. So here pink lines represent the output and dotted lines represents the input. Second one is natural sampling. It is also called as gating. It is also called as gating. Okay. So already we discussed that it is very difficult to generate series of impulses. It is very difficult to generate a series of impulses practically. So that's why instead of impulses, instead of series like impulses, a pulse train is generated. Okay, so it is difficult to generate a pulse of width 0, ante impulse generate cheyadam difficult. Okay, so pulse of specified width, it is easy to generate practically. So we can ante simply to say natural sampling is same as ideal sampling but in a practical manner. Okay, natural sampling, the working principle behind the natural sampling is same as that of natural sampling in a practical manner. So practically it is difficult to generate impulses. Okay, it is generated to impulses, it is very difficult. So natural sampling is used. So natural sampling is the same technique, same as that of, the working principle is same as that of ideal sampling, but instead of impulses, series of pulses are generated, that is xp of t. Okay, x delta of t is series of impulses, xp of t is series of pulse train. Okay, pulse train is xp of t and the principle is same. What is that principle? Whenever x of t is multiplied by xp of t, what is xp of t? Series of pulse train, or simply you can call it as pulse train or series of pulses. Pulse, how can we relate the pulse with impulse? A pulse with like negligible, you can say negligible width is generally called as impulse. Okay, so for ideal sampling it is, so please go through the points here. This is the non-ideal approach, or you can also call it as practical approach. Practical approach that uses rectangular pulse train, instead of impulse train. Instead of impulse train, rectangular pulse train is used here. And for ideal sampling, it is difficult to generate impulse train practically. Okay, so that's why we are using natural sampling, and why it is also called as gating, because you are using a rectangular pulse train, rectangle and gating. Okay, so that's why it is also called as gating. So please observe the figure. Okay, x of t is multiplied with xp of t to generate xs of t, that's all. Okay, where xp of t is shown here, it is a series of pulses located at, amma okkasari meer ikkada observe cheyalsindi entante, xp of t is a series of pulse train, and once again these series of pulses are located at sampling intervals only. Okay, but the pulses are of width tau. So what is the width of each pulse? Tau, and these pulses are located at sampling intervals once again. Okay, NTS దగ్గరే ఉంటుంది, where n ranges from minus infinite to plus infinite. So this is the output. So what is the output? X of t is multiplied with xp of t to generate xs of t, where xs of t is the natural sampled result. Here if you observe, pink figure represents the xp of t. Pink figure represents the sampled signal. So that sampled signal, if you observe the pink pulses in the output, its amplitude naturally varies with respect to the analog signal. That's why it is called as natural sampling. Its tops are not at all flat. The amplitude of the pulses are not flat. The amplitude of the pulses are natural, and these continuously varies with respect to the analog signal. with respect to analog signal. Okay, so that's why it is called as natural sampling. Is this slide okay to everyone? Please, one of you respond. Is it okay?
Yes, ma'am.
Okay, ma, thank you. So this is the time domain description and frequency domain description of natural sampling. How can we generate natural sample signal? X of t is multiplied by series of pulses. X of t into xp of t is xs of t. How can you generate, please observe the slide. How can you generate xs of t? By take the product of x of t and xp of t, where xp of t can be defined as series of pulses or series of rectangular amplitude pulses. Okay, that you can represent as a Fourier series. Okay, you can represent the series of pulses in the form of Fourier series ranging from minus summation minus infinite to plus infinite Cn into e power j 2 pi n fst, where Cn is the Fourier series coefficient. Okay, this is the time domain description. So what is the time domain description of natural sampled result? Multiply x of t with xp of t. What is the time domain description of ideal sample? X of t into series of impulses x delta of t and chapter. Okay. So and next, this is about the Fourier series representation. Apply the Fourier transform to the time domain description. Okay, so you will get shift in the frequency. You will get shift in the frequency because in the time you are multiplying with exponential term. Time domain lo shift unte meeku in the frequency domain you will have multiplication in the with the same exponential term. Alane if there is multiplication in the time domain with the exponential term, you will have shift in the frequency because you can go through the Fourier transform properties. Okay, if there is any shift in the time, the same will be replicated as the product of exponential term in the frequency. If the product is there of exponential term is there in the time domain, you will have shift in the corresponding frequency in the frequency domain. Okay, so anyhow we can continue the sampling in the next session because time is going on. And one more thing that I want to mention you is that, so class started by 9:30, but only by the time only 18 students attended. Okay, kindly from the next class onwards please join by 9:30. Okay, ఎందుకంటే attendance maybe sometimes it will take from the from 9:30 onwards. Okay, so to avoid such kind of discrepancies, please join by 9:30 or at least 9:32, 9:33. Okay, don't move up to 9:40 like that. Okay, so I think in the today's session what we discussed, in the today's session we discussed the basic PCM, okay, the PCM elements, and in the PCM elements we have started with the first one, that is sampling. We discussed three types. We discussed only two types, ideal and natural sampling and flat top sampling, and the continuation the derivational part we can see in the next class. Okay, I will wait, I will take the attendance, and any doubts you can ask